Hey guys, we've now looked at several sections with different structures that we're looking for when trying to integrate. If we happen to have a composition of functions, U substitution will probably work for us. If we are looking at a product of functions, integration by parts can work for us. Today we're going to look at several other structures, the square root of a squared minus x squared, the square root of a squared plus x squared, 1 over the square root of a squared plus x squared. And all of these guys use a technique called trigonometric or just trig substitution to solve them. So if you're thinking to yourself, gosh, I have no idea what sine or cosine or tangent is, this is your chance to dust off an old notebook, old textbook, or use Khan Academy to review those topics. So let's see when this would come into play. Well, for my first example, let's study this guy, the square root of 1 minus x squared dx. So first off, I want you to note that it's of this form, right? Because in this case, we can let a equal 1, and that would be the situation we're in. Second, let me say that this is actually something we've seen before when we were first doing areas. This guy happens to be the top half of a circle. So if you wanted to do the definite integral of this, again, from way back when, if I wanted to integrate, for example, from minus 1 to 1, it wouldn't be a problem because it would just be half the area of a circle with radius 1. Things become a little bit more dicey if I want to go from, say, I don't know, how about from minus 1 to 0.7? Well, then we don't really have a formula for it. So we want to be able to integrate things like this so that we can find any area or portion of an area of a circle. Before I dive into this guy, let's come up with a process that we can use. And the process is as follows. If you have any function of x, so if we want to integrate f of x dx, then that's equal to big F of x plus c. Then I'm going to make this interesting substitution. I'm going to let x equal sine of theta. Well, if I do that, then this is the same thing as big F of sine of theta plus c. So I'm going to give yourself a second. Can you think of what you would have to integrate to get that? Right, so hopefully you put little f of sine of theta times cosine theta. In other words, probably an easier way to think about it than the way that I asked it is that the derivative of big F of sine of theta is little f of sine of theta times cosine theta. Why? Because of the chain rule. Derivative of sine is cosine, the derivative of big F is little f. So if you think about it, what we could do is as follows. So if we want to get from here to here, then the streamlined process is if we let x equal sine of theta, dx is then cosine theta d theta. And we can once again, just as we did with the U substitution, visually match up the pieces. So that's what I'm going to do over here. So let's let x equal sine of theta. And then once I do that, I'm stuck. Dx is just cosine theta d theta. And then I'm going to get something in the form, f of sine of theta times cosine theta. So in other words, this guy is the integral of the square root of 1 minus sine squared theta. Just plugging that in there. And dx is cosine theta d theta. So I want you to stop the video for a second and ask yourself, is this easier than this to solve? And how would you solve it? Right? Hopefully you said to yourself that 1 minus sine squared theta is cosine squared theta, right? Because we have that cos squared theta plus sine squared theta is 1. So 1 minus sine squared theta is cos squared theta. So this is the integral of the square root of cos squared theta times cosine theta. Square root of cos squared is going to be cosine, and times another cosine is cosine squared theta d theta. So at this point, we actually have two options in solving this. Let me just tell you both, and then I'll tell you which one I would recommend. Cosine squared theta is cosine theta times cosine theta. So you could actually do integration by parts on this one. But I think an easier way to do that is to know that there's a trig identity which says that cosine squared theta is 1 plus cosine 2 theta over 2. In fact, let me tell you the two of them that are going to pop up. Cosine squared theta is 1 plus cosine 2 theta over 2. And sine squared is 1 minus cosine of 2 theta over 2. So hopefully you remember at least bumping into them when you took pre-calc. So why would I do it this way? Well, once I do it like this, let me pull out the 1/2, and I have the integral of 1 plus cosine of 2 theta d theta. I could then break this into two integrals. And after breaking this into two integrals, I could just do basic integration here, so 1/2 theta plus 1/2, and then I can do a u sub on this guy. So let me do that over here as an aside. So I'm integrating cosine of 2 theta d theta. I'll let u equal 2 theta. du is equal to 2 d theta. So then this guy is the same thing as the integral of, let's see, cosine of u du, where I guess the d theta piece is 1/2 du. So I need the 1/2 there. This is 1/2 sine of u plus c, or 1/2 sine of 2 theta plus c. So integrating this guy, I get 1/2 sine of 2 theta plus c. Before I go on, I want to take 2 seconds for us to realize something. I did a u substitution on cosine of 2 theta. And 2 theta has a special property. The inside guy for the u substitution happened to be a linear function. Now watch what happens with linear functions. U equals 2 theta, du is going to equal 2 d theta, and then the 1/2 is going to come over here. So what happened is our result was just 1 over the slope of the inside guy. So when I integrate functions of linear functions, the way I do it is I actually do it on my head, and I do it as follows. I integrate or find an antiderivative for this guy, leave the inside guy, and then just multiply it by 1 over the slope. So actually, before continuing with this, I want to show that to you guys with one other example. I think it's super useful. So see if you can do this one in your head without writing out all the details based on what I described over here. So hopefully you're saying, oh, okay, so it's just going to be e to the 3x. And then again, we'll have u equals 3x, so that du is 3 dx, and then the 3 comes over to the other side. So it just becomes 1/3 e to the 3x plus c. So again, you might need to rewind the tape and think about that a little bit. But from now on, if I ever have a linear function up here, I'm just going to take the antiderivative, keep that guy inside, and multiply it by 1 over the slope. back to what we have here. We have 1/2 theta plus 1/4 sine 2 theta plus c. Well, that's great, except my question up here was in x's. So I want to convert these thetas back into x's. Well, do we know what theta is? We know that x is sine theta, but that's true if arc sine of x is theta. So again, arc sine is the inverse function of sine. If you forget about that, you want to check that out, do a little bit of Googling, something you would have seen in differential calculus. So arc sine of x is theta, so this is 1/2 arc sine of x. Well, what about sine of 2 theta? What about sine of 2 theta? I know sine of theta is x. Well, there's another trig identity that you learned probably way back when, which is that sine of 2 theta is 2 sine of theta cosine of theta. So this is another trig identity. Let me tell you now, I don't expect you guys to have these memorized, but you should be aware of them because the ones that I'm illustrating now pop up in this section. And let's see if we can finish this with the information we have. This is arc sine x plus, I guess that's just 1/2. What is sine of theta in terms of x's? Go back up here. We just get x back. And now I'm stuck. I need to figure out what cosine of theta is. So for some of these problems, not all of them, you have to use another technique that you learned in pre-calc. Some of you may have seen it in calculus, in applications of the chain rule, and that is using a triangle to develop one of these other trig relationships. So in other words, I'm told that sine of theta, which is opposite over hypotenuse, I'm told that sine of theta is x, aka x over 1. But if this is x and that's 1, then by the Pythagorean theorem, that side's going to be the square root of 1 minus x squared. That's because this side squared, if I call that a, plus this side squared is equal to that side squared. So a squared is 1 minus x squared, and we get that that side is the square root of 1 minus x squared. Sorry, I see that's cut off. There we go. All right, so what? Well, we're looking for cosine of theta, and now I can get it from this triangle. Cosine is adjacent over hypotenuse, so it's just the square root of 1 minus x squared over 1, or I could just write it as the square root of 1 minus x squared. Let me add my plus c, and I am done. The derivative, if you took the derivative of this crazy thing over here, you would get the square root of 1 minus x squared. So let me highlight the steps in these problems. They are definitely the most involved type of integral. So let's highlight and see what we did. So if it's of the form a squared minus x squared, we let x equals sine theta. Once you decide that, dx is cosine theta d theta. And the reason for that was that little proof that I had put up earlier. Then you put everything in terms of thetas. That's what we did over here. Then we integrate it. After we integrate, we put everything back in terms of x's, and that's the final answer. All right, let me do a slight variation of this problem to illustrate what else could potentially happen. Let's check out the integral of 1 over the square root of 16 minus 4x squared dx. So first off, this doesn't exactly look like this guy, but it kind of looks like 1 minus x squared. And we saw that if we let x equal sine of theta, that this could turn into potentially some sort of cosine. However, we need it to look like, again, 1 minus something squared. So since I need a 1 here, let me factor out a 16 first, so that this becomes the integral of 1 over the square root of 16 times 1 minus 4 over 16, 4 over 16 times x squared. So let's clean this up a little bit. Before we do though, make sure you believe this. 16 times 1 is 16. 16 times minus 4 over 16 is minus 4. So again, I'm going to clean it up. So this is, let's see, the square root of 16 is just 4. And this is the same thing as x squared over 4. So I want this to look like 1 minus blah squared, and then I'll let my blah equal sine of theta. So what do I mean by that? If this is x squared over 4, then the thing that I'm squaring is x over 2. Then I can let x over 2 equal sine theta. Can you guys see by doing that, this becomes 1 minus sine squared theta? Yeah, that's good because once again, we'll be in the world of cosine. Well, if x over 2 is sine of theta, then I guess x is 2 sine theta. And my dx is 2 cosine theta d theta. So let's see what we have. So this is equal to, well, I'm going to pull the 1/4 out because it's just a constant going along for the ride. And this is 1 minus sine squared. My dx is 2 cosine theta d theta. So let me give you a second. I want you to simplify that. Right, after simplifying it, hopefully you took a second to try to do that. 2 times 1/4 is 1/2. And watch this. We have cosine theta. The square root of 1 minus sine squared is the square root of cosine squared, which is just cosine. Beautiful. So this horrific looking integral, it's just the integral, 1/2 the integral of 1 d theta or d theta. The integral of that is just theta plus c. And how are we going to get theta? We go back here and we realize that x over 2 is sine of theta. So I guess if I wanted theta, I could take the inverse sine of both sides, or arc sine. And that will be the same thing as theta. So again, let me actually write that out. X over 2 equals theta. That's true if and only if arc sine of x over 2 is theta, because those guys are inverse functions. So what we've seen here then is if it just so happens that we're not quite 1 minus blah squared, we can make that happen. So we saw that through this example. So we just used a little bit of algebra to put it into the correct form. All right, let's check out another example with plus. So let's say we have 1 over x squared plus 1 dx. Again, not exactly in any of these forms, but it's close to this one. And we'll see why with radical or without radical, this will be helpful. So hopefully at least some of you know that I don't even need to do any work on this thing because this is a basic formula. The derivative of the arctangent from differential calculus is 1 over x squared plus 1. But let's say we forgot that, which is probably most of you. Let's say we forgot that. Let's see how we would solve that using this method. So first, I want to note that sine squared plus cos squared is 1. So if I divide everybody by cosine squared, I get tangent squared. Sine squared over cos squared is tangent squared. Plus cos squared over cos squared is 1. Equals 1 over cosine squared, which is secant squared. So we have another relationship. Look at this, and tell yourself what you should make your substitution to be. So hopefully you said let's let x equal tan theta, because if we let x equal tan theta, this thing on the bottom is going to become secant squared theta. But if x is tan theta, the derivative of tangent is secant squared d theta, and that's from differential calculus. So let's see what we have. So I guess this guy is the integral of 1 over tan squared theta, 1 over tan squared theta plus 1, dx is secant squared theta, d theta. Tan squared theta plus 1 is secant squared theta. So we have secant squared theta over secant squared theta. So we have the integral of 1 d theta, which is theta plus c. Going back here, we see that x is tangent of theta. X is tangent of theta. So I guess that arctan of x is theta, because again, tangent and arctangent are inverse functions, and we get arctangent of x, which is what we thought we would. So moral of the story is if you ever have some number squared minus x squared or stuff squared, you're going to use x equals sine theta. If you have number squared plus x squared or stuff squared, as we'll see in a second, you're going to use x equals tan theta. So in summary, let me write that down. So I'm going to write a squared minus stuff squared, that tells us sine theta. A squared plus stuff squared, that tells us tangent theta. Let's do one final example. So let's take a look at, well actually, sorry, two more examples. So give this one a shot at home, and then press play. Right, so hopefully some of you saw that this one could be solved not using trig substitution. And this is a very important point that I want to make. Hopefully you guys realize that trig sub takes a long time to solve. You could solve this one by trig sub, but there's a way easier solution. If you let u equal x squared plus 1, du is 2x dx, boom, we're pretty much done. Because then this becomes, let's see, the x squared plus 1 is 1 over u. The dx times the x is 1/2 du. So we get 1/2 ln absolute value of u plus c, or 1/2 ln x squared plus 1 plus c. I don't actually need the absolute value because x squared plus 1 is always positive. So I do want to make the point at this time that you're developing several methods in solving these things. When you can do a u substitution, do a u substitution. It's probably the easiest of the techniques that we've looked at. Trig sub is the toughest, but sometimes you have to use trig sub. All right, so let's do one more example, and this one I promise we are going to use trig sub to solve. Let's take a look at the integral of 1 over x squared times the square root of x squared plus 4 dx. So again, I'm going to ask myself, now that we open our minds to the idea, I'm going to ask myself if I can do u substitution here, and unfortunately it's not going to work. It's also not an integration by parts problem, so then I'm going to start looking at trig substitution. It looks like I have number squared plus x squared, so this looks like a candidate. It looks like the tangent is going to work for me, but in particular, it's not x squared plus 1, so I'm going to have to play that game that I played earlier and turn it into 1. So this is the same thing as the integral of 1 over x squared times the square root of, so let me factor out the 4. I factored out the 4, and Let me pull this square root of 4 out. That's just 1/2. So we have x squared. There's the square root of x squared over 4 plus 1. And again, I want to make the stuff equal to tangent of theta, so then when that stuff is squared and I add 1, it gets to be secant squared. So instead of x squared over 4, I'm going to write this as x over 2 quantity squared. So hopefully you believe that x over 2 squared is the same thing as x squared over 4. Now I'm going to let x over 2 equal tangent of theta. Why? Because then tan squared plus 1 is going to be my secant squared. So we have that x is 2 tan theta. So that dx is 2 secant squared theta d theta. So this is the same thing as 1/2 the integral. Well, let's see, x squared is 4 tan squared theta. That's this piece. This guy is the square root of tan squared theta plus 1. That's that piece. Dx is 2 secant squared theta d theta. Whew. All right, well, let's see what we have here. I guess this 2 and this 1/2 cancel. I have a 1/4. Let me pull that guy out. I have a tan squared on bottom. And then this guy again is secant squared theta. We're taking the square root of it, so that's just secant theta. I have secant squared over secant, which is just secant d theta. All right, at this point, I invite you to pause the video and try to solve this integral, which just involves trig. You might need a little bit of time, but give it a shot. And when you're done, please press play. All right, the way that I approach this, and I'm not saying it's the only way, there might be other ways, is I converted everybody back to sines and cosines. So secant is 1 over cosine. Tan squared is sine squared over cos squared. So this is 1/4 the integral 1 over cosine theta times, let's flip the bottom, cosine squared theta over sine squared theta d theta, which is 1/4 the integral of cosine theta over sine squared theta. So I just canceled one of those cosines. So what do we do now? I would recommend pausing the video again, see if you could think about it. All right, well, I'll tell you what we're going to do. We're going to turn this into a u sub question. So let's let u equal sine theta. Then du is cosine theta d theta. So that this is 1/4 the integral of, let's see, cosine theta d theta is my du. This is just 1 over u squared, or u to the minus 2. Boom. That is the integral that I'm actually going to have to integrate. So we got 1/4 u to the minus 1 over minus 1, which is the same thing as multiplying it, plus c. So we have minus 1 over 4u plus c. But we don't want things in terms of u's. We want things in terms of x's. Well, let's see. U is equal to sine theta. So this is minus 1 over 4 sine theta plus c. But what's sine of theta? Now we have to go back here because we want to write it in terms of x's. And here, once again, we'll use that triangle trick. So we have theta. We know that the tangent of theta is x over 2. So that means that opposite over adjacent is x over 2. And we have that a squared plus b squared. A squared plus b squared is c squared. So this is minus 1 over 4 times sine of theta. Sine of theta is opposite over hypotenuse. And if we want to, we could simplify that a little bit by flipping this over to get minus the square root of x squared plus 4 over 4x plus c. All right, so that is trig substitution. Lot of steps. Keep your wits about yourself. Again, just to summarize, how the heck did I get from point A to point B? I realized it was x squared plus a squared, so I thought it was going to be some sort of tangent. And I had to make it in the form 1 plus blah squared, so that's what I did here. Then I put everything in terms of theta. Then I had to figure out how to integrate it. Well, this I had to be a little bit sneaky to turn those guys into sines and cosines. I then used a u substitution. I then converted it back into x's. All right, and that is all I have to say about trig substitution. Thanks for listening.